Good morning, dear students. My name is Ferhan Mazher, and today is 30th October 2021, and the day is Saturday. Right now, I am with the 11th Cambridge class, and the subject we are studying is Physics 5054. This is Cambridge O-level physics, and today we have set our hearts to solve an ATP paper, alternative to practical. We call it paper 4. And today we will solve October-November 2019 paper. This paper belongs from zone 2. So let's start this paper. So on your screen, let's start. So here comes the paper. October-November 2019, 4-2 paper. Okay, so a student in a laboratory investigates how the length L of a spring varies when different loads, capital L, are added to it. He sets up a spring in a clamp with a load of 1 Newton attached to its lower end as shown in the figure 1.1. Measure the length L of the spring shown in the diagram in the figure 1.1. Do not include the loops at each end of the spring in your measurement. Record your answer in the table 1.1. It's a 1-mark question. So what you will do, you will start from here and till here. So you will measure this length. That will be the length which you are supposed to measure. So what you will do, you will put a scale on this figure, and you will measure it, and it will be so measure it from your diagram. If you have the hard copy with you, and whatever the answer you get, just note it down in the table 1.1. So let me show you. Okay, so this is like this. When 1 Newton load is hung, the length will be 66 millimeter. The length will be 66 millimeter. I have done that thing. So that's why you will get this. And the next question is on the diagram in the figure 1.1, draw a ruler in the correct position for the student to measure the length L in the laboratory. Okay, so we have to draw. Okay, so here you can see that I have drawn a scale. I have drawn a scale which is the scale is vertical, and it's with that spring, and with this ruler we can measure the length of that spring. So this is how you have to draw that ruler. That is question number A, second part, and it was 1-mark question. You have to draw this ruler. So the second and third part is the student determines as accurately as possible the reading on the ruler at the bottom of the spring. On the figure 1.1, mark with an X the position of the student's eye. The student's eye should be in level with this position, okay? So you can see that here I have positioned the eye and I have marked this level, this point as X. So this was question number A and its third part. So we are moving to the next part. He says, that's the B part, and let's go to the question paper again. Okay. So this was all the questions which we have done, and this is that second portion. So in the B part, he says the student varies the load and takes a series of measurements of L and L. His results are shown in the table 1.1. State one way to improve the table of results. So if you look at this table carefully, here is 1 Newton load, then 3 Newton load, then 5 Newton load, then 2 Newton load, then 4 Newton load. So one thing you will notice that the load is not in the correct order. So for example, if one good thing they can do is they can place this load in proper ascending order. For example, 1 Newton load, then they should note down 2 Newton load, then they should do their observations for the 3 Newton load, then 4 Newton load, and then the 5 Newton load. That will make more sense. And so I can write my answer. Let me show you my answer about this question. Okay, so here is my answer. I've written here the list readings in column of load in order of increasing load. Okay, so the load should start from the lowest load, and then the next high load, then the next, and the next, and the next. So the load should be put in order. Either you can write them in the increasing order or decreasing order, whatever you like. Okay, the second part is, let's go back to the question. Here we have this question. He says, let me increase the size so you can see the whole question. He says, on the grid in the figure 1.2, plot a graph L. L means the load on the y-axis against the small l, which is the spring's length on the x-axis. Start both the axes from the origin, which is 0, 0. Draw the best fit straight line. Okay, so this is the 4-mark question. So it's a 4-mark question. So this is that graph given to us, and on the y-axis I will put the load, and on the x-axis I will put the length. And this is that table. Okay, so this is that table. So let me show you how I have done this. Okay, so we are done with this. Okay, so you can see that they have asked us to label. First of all, I will label the the axis. On the y-axis, we will put capital L, which will be in newtons, and that is the load which we are hanging with the spring. And on the x-axis, we will put the length of the spring, and that's in the millimeters. And the scale I have chosen because the length is going up to 298. So the scale is that 2 centimeter represents 40 millimeters. So 40, 80, 120, 160, 200, 240, 280, 320. So this is very important. You chose your scale, and then you label both the axes. On the y-axis, we have put load, and on the x-axis, we have put the length of the spring. Okay, now you can see that we have plotted those graphs, and I can tell you this point here is when the length is 66, the load is 1 Newton, and this point is when the length is 100, the load is 2 Newton, and this is when the length is 130. So when the length is 130, the load is 3 Newton, and when the length is 163, this point, 163, and the load is 4 Newton, and here at this point, the length is 198 and the load is 5 Newton. So you can see I have plotted those points here, and when you have plotted those points, so these are the 1, 2, 3, 4, 5, 5 points, and we have used that table. Okay, so the next question coming up on your screen is, then it says, and then they ask us to draw the line of best fit. You can see here, I have drawn the line of best fit, and you can see that I have made sure that this line is in the same pattern as these points are. And the main point is not to join the points. The actual thing is the number of points which are above the line of best fit, the same number of points should be below the line of best fit. I have tried to draw a line of best fit. So you can see 2 points are above this line and 2 points are below this line. So approximately is the line of best fit. You might be able to draw a little better line of best fit. Okay, so he's asked us to draw the line of best fit. So the 4 marks, that was the question number 4, question number 1B, second part. It was a 4-mark question, so we are done with that question. So let's move to the next question. He says, state whether L is directly proportional to L. Explain your answer. So I can say, if you look at this graph, and this is the capital L, this is the small l, and the graph is a straight line with the positive gradient, but the L, the load and the length, they are not directly proportional. Why I'm saying, you can say it from the graph, because any 2 quantities which are directly proportional to each other, their graph always passes from the origin. So this graph is not passing through the origin is here, so this graph is at this point. So if the graph would have passed through the origin, then we can say that they are directly proportional. But right now, they are not directly proportional because the graph is not passing through the origin. So I have written this answer. You can see that the L is not directly proportional to L because the length is not directly proportional to the load, because the graph is not passing through the origin. So it's a 1-mark question. And then the 4th part of the question number 1B part is, he says, use your graph to determine the length L naught of the unstretched spring. So when the spring is not stretched, you can see when the load is 0, here on the y-axis you have the load. When the load is 0, so what's the length here? That's 36 millimeter. So when there was no load on the spring, so then its length, that's known as L naught, unstretched length. When the load is 0, the length is 36 millimeter. And this I have told from the line of best fit. I have extended the line of best fit, and you see from there I can tell when it cuts the x-axis, the load will be 0 at that point, and the length is 36 millimeter. Okay. Then the C part is coming up on your screen. He says, use your graph to determine the L naught of the unstretched spring and show your graph how you did this. So on the graph, I told you that how I've done this. So that's 36 and millimeter. Then the C first part is use your graph in the figure 1.2. Determine the extension E of the spring for a load of 3.6 Newton. So you can see when the load is 0, the length is 36 millimeter. And when the load is 3.6 Newton, the load is 156 millimeter. So the extension the formula for the extension is L minus L naught. L means the length at a particular load, and L naught means the length when the load is 0. So 156 minus 36, that will be 120 millimeter. So the extension is 120 millimeter, and I have used the graph. You see at the 0, the length is 36. And when the 3.6 length, 3.6 is here, 1, 2, 3, 4. So the 3.6 is here somewhere. So this point. So that is 156 millimeter. So the length is 156 millimeter at the load of 3.6. So the extension is 120 millimeter. You can see the formula we have used. Extension is equals to L minus L naught. So that was this question. Now we move to the next question. He says, let me go back to the question paper so you can check the questions also. So this was that question where they have asked you to draw the grid and then the graph. So this is that question, okay? So we were working on this question, and you can see that we have answered this question, we have answered this question, we have also answered this question, and that the first part was, the third part was 1 mark, fourth part was 1 mark. Question number C 2 marks. We are done with that. Then we have this next question. It says, this is C, second part. On the axis in the figure 1.3, sketch a graph of L against E. So here you have to put the length, the load and the extension, and the length, the load, sorry, I again say length. The capital L is representing the load. The load and the extension, they are directly proportional to each other. So there will be a graph here. If you want to draw the graph, that will be a straight line passing through the origin. So let me show you. I have drawn that. I think I have drawn. So I think I just missed it. So give me a minute and I will place it here. And you can see that this is that graph. So the load is on the y-axis and the extension is on the x-axis. And we know that the load and the extension, they are directly proportional to each other. So their graph will be a straight line passing through the origin. So this is question number 1C and its second part. So let's go to the next question. What is the next one? That was a 1 mark question. Here he said that the gradient of your graph in the figure 1.2 measures the force constant of the spring. The greater the force constant, the harder it is to stretch the spring. So the slope of the graph in the figure 1.2, that is equals to the force constant of the spring, or we normally say constant of the spring. And the second spring has the same unstretched length, but a greater force constant. So using the same axis, draw on the figure 1.2 a line to show how the length of this second spring changes as loads are added to it. So because the K value or the greater force constant is greater for the spring number 2, so for the same loads, it will produce less extension in the spring 2. So whatever is the length extension or the length which is achieved in the load spring number 1, the spring number 2 will get less length. There will be less extension because it's the force constant is greater. So let label this line as S. So using the same axis, draw on the figure 1.2 a line to show how the length of second spring changes as loads are added to it. Label line S. Okay, so let me show you. So you can see this red color line is the spring number 1. This was already drawn on the figure 1.2. This blue color line, I have drawn it, and I just make, you can draw this line by keeping in just 2 points. That this blue line, its starting point will be the same point because it's unstretched length. When the load is 0, its length is also 36 millimeter. And when you apply load to the spring number 2, the extensions will be less. So the length of the spring will be smaller for the same load as compared to the spring number 1. So you can see the blue line that represents the spring number 2, and you can see that we have labeled blue graph S. So that's it with the question number 1. It's a 15 mark total question. Hopefully you have understood. And so let's check them first of all. Okay, so we are done with the question number 1. Now I am showing you the marking scheme of this paper. So this is the marking scheme. Number 1 is showing up on your screen. So what you can do up to question number 1B, third part, stop this video. Pause this video and take your time with this. Okay, so I'm moving to next. These are the rest of that whole of the question. It's very important to check the marking scheme. And remember, it's very important. Okay, so, normally whenever I do questions, I solve paper, I check my answers, I compare them with the marking scheme. And this is what we try to teach our students also. So that they should always check their with the marking scheme. They should compare their answers with the marking scheme. Okay, so let's move to the next question. And the next question coming up on your screen is question 2. So here we go. Student does an experiment to measure the density of water. She places an empty test tube on a top pan balance as shown in the figure 2.1. Record the mass M of the test tube to 3 significant figures. So up to 3 significant figures, here it is 1, 3, 5, 6 gram. So it's 13.56 grams. But if you round it to the 3 significant figures, that will be 13.56. So it's very important to note down. He said 3 significant figures. So basically this reading is 13.56 gram. But if you round it off to 3 significant figures, then it will be 13.6 grams. So let me show you my work. I have not written it 13. I have written it 13.56, but this answer should be, let me insert here my answer. So up to next one. So this reading should be 13. Reading should be 13.6 gram. Okay, so the reading should be 13.6 gram. That is the 3. I have not rounded it off to significant figures here, but in 3 significant figures, it will be 13.6 gram. So hopefully, let me increase the size so you can see the whole thing. So this is how you do this. And so that was the question number 2, and it's A part. You just have to record the reading which was showing up on that pan balance, electronic pan balance. Okay, so the question number 2 and its B part is, she says she pours a volume V1 of 65 cubic centimeter of water into a measuring cylinder, and she lowers the empty test tube to the water in the measuring cylinder so that it floats. Figure 2.2 shows the new reading on the measuring cylinder. So if you pay attention, the reading here is, so this is 60, so this will be 70, and this is 80, so 72, 74, 76, 78. So the reading is between 78 and the 80s. The reading will be 79 centimeter cube. So the reading is 79 centimeter cube. Okay, so we are moving to the next part, and so that's the so the question number 2 is B, and its second part. It says calculate the increase in the volume reading V in the measuring cylinder. So the increase will be V2 minus V1. V2 is 79, the final volume, and the initial volume is 65. So it will be 14. So the volume will be 14 centimeter cube. Then he says suggest one source of experimental inaccuracy in the reading the scale on the measuring cylinder. You see, normally what happens here, you have water. So water's lower meniscus is always, we check the level of the water by its lower meniscus. So the one particular experimental error can be that somebody might not be reading the bottom of the meniscus. Meniscus is the level of the water in the test tube or the measuring cylinder. So it's like a moon, the crescent, and we always take the bottom of the meniscus. Okay, so somebody might not be taking from the bottom of the meniscus. Then the C part is that he says theory suggests that the density rho of the water is given by the equation density is equals to mass divided by volume, or we say rho is equals to mass divided by this letter that is called rho, and this represents the density. So the density is equals to mass divided by volume. So use your answer to A part and the B second part to calculate the density, state the unit of your answer. So we know that the mass of and the mass is 13 of the test 13.56 gram. The mass of the test tube is 13.56 gram. If you round it off to three different figures, it will be 13.6 gram, and you divide it with the volume, that's 14 centimeter cube, you get 0.97 grams per centimeter cube. That's 0.97 grams per centimeter cube. So we are done with the question number 2, and this question was of 6 marks. Hopefully you have understood that how we are doing this question. So let's check the marking scheme. It's very important to once you are done with the question, and then to check the marking scheme. Okay, so here on your screen, the question number 2, its marking scheme is showing up. You can pause the video and take your time with the marking scheme of the question number 2. It's showing up on your screen. Okay, so we are into the next question, and we are done with this question. So this was that question number 2. It was totally of the 6 marks. Now we are going to the next question. The next question coming up on your screen is, he says, a student investigates the resistance of different lengths L of a metal wire PQ of the total length 1.000 meter. She sets up the circuit shown in the figure 3.1. She places the sliding contact S at a distance L equals to 10 centimeter from the end P of the wire and records the reading on the ammeter and the voltmeter. The reading on the voltmeter is shown in the figure 3.2, which you can see. Read the voltmeter scale and record your answer in the table 3.1. So here we have a table 3.1 where I have to record what's the reading on the voltmeter. I will record it here. And okay, so let's increase the size a bit. Okay, so you can see this is the voltmeter. So this is 0.51 and this is 0. So it will be 0.1, 0.2, 0.3, 0.4, and that's 0.5. So the reading is 0.11. So no, sorry, this is 0.1, this is 0.2, so this is 0.3, 0.4. So this reading is basically 0.2, 0.21. So the reading is 0.21. So 0.1, 0.2, 0.3, 0.4, 0.5. So the reading is 0.21. So I will record this in the table. So let me show you my answers. Okay. So you can see here, I put it down 0.21 volt, and then it's so the reading of the voltmeter is 0.21 volt, and the current is 0.25 ampere. So very easily you can find the resistance. You know the formula is given here. The R is equals to V by I. So in your calculator, divide 0.21 with the 0.25, and you will get 0.84 ohm. So the resistance will be 0.84 ohm. So this was the question number A and its second part. That was the question number 3A, its second part. So let's move to the next part. It says, here we have. The student repeats the procedure for the length of 20 centimeter and length of 40 centimeter wire and records her results in the table 3.1. Look at the results in the table 3.1 within the limit of experimental error suggests that the relationship between L and R. If you look at this table carefully, you see when the length is 10, the resistance is 0.8. When the length is 20, the resistance is 1.64. So when you have doubled the length, the resistance also has approximately doubled. So you can say when you double the length, the resistance also doubles. So if this kind of relationship is between two quantities, we can say that they are directly proportional to each other. So you can see R and L, the resistance and the length of the wire are directly proportional because the length doubles, the resistance also doubles. So it was a 2-mark question. Then we have the C part. He says the student notices that the wire is warm at the end of the investigation. Describe one precaution that the student can take to minimize this heating effect. You see, when the current passes through the wire, due to the resistance of the wire, the electric is converted into heat energy and temperature of the wire starts increasing. And that can change the resistance of the wire. That can have effect on the resistance of the wire. So to avoid this, one thing which you can do when you have set your apparatus close switch and start the current flowing through the circuit, immediately note down the reading on the ammeter and on the voltmeter and note them in your and switch off. So you keep the switch closed for a very short time and then you immediately switch off. So this will avoid the heating of the wire. I have written the answer, the C part. He says switch off once you have taken the readings. Okay, so that was the question number 3 and it was of 5 marks and hopefully you have understood this. So let's check the marking scheme. So let's have a look at the marking scheme. So here you see, here we go. So the question number 3 is marking scheme is showing up on your screen. One thing you can do is you can pause this YouTube video and take your time with the marking scheme. And I always tell my students that it is very important that when you have done a question to check it with the marking scheme, to compare your answer with the marking scheme. And okay, so let's move to the next question. And the next question is question number 4. So the question number 4 is going to show up on the screen. So this was that question. Now we are going on to the question number 4. So let me reduce the size so you can see the whole question. A student investigates the refraction of light by a right-angled glass prism WXY. He uses a ray box to direct a ray of light to side WY of the prism as shown in the figure 4.1. He places 2 pins P1 and P2 on the incident ray and marks each position with a cross. He places another 2 pins P3 and P4 on the emergent ray and marks each position with a cross. He removes the ray box. He draws around the outline of the prism and then removes it. The student uses a ruler. Okay, so we are here. The student uses a ruler to trace the path of the ray until it reaches the side WX of the glass prism. He labels the points where the ray hits the side WX with the letter Z as shown in the figure 4.2. Question number four, and it's A, and first part is draw the nut to the prism at the point Z. So it's very easy question. Let me show you how I have done this. And okay, so here we go. So if you want to draw the normal point Z, you can see here I have taken my protector, and the crosshair of the protector is at the point T, and this zero lines of protector, they are on the line XW. This point is a little off, it should be exactly on the Z. And then what I will do, I will dot here at the point where it shows 90 degree, and then I will join that dot with this Z point with a ruler, and that will be the normal. I will prolong it, and that I will draw it, I will make it a dotted line, and that will be the normal. So let me show you. Okay, so here you can see that I have put that red colored line, dotted line, and this is the normal. So that was question number 4A, first part. Then we have the second part. He says use a ruler to draw the path of the ray from the Z until after it emerges from the prism. So here we have that pin 3 and pin 4, they are on the emergent ray. So let's learn my technique that I have first joined these pins. They are pin 3 and pin 4. So I will join these crosses until they touch this position on the line XY. So here you can see that I have drawn that emergent ray, and then I will join this point with this point with the help of a scale. So you can see I have placed a ruler here, and then I will draw a line here. So here you can see I have drawn that line. So this is the path. This is how that path will be formed. Okay. So then the B is then we have the B part. He says describe the overall effect of the prism on the direction of the ray. So if you look at the ray was going towards the top of the page, and here after the refraction, the ray is going towards the bottom of the page. So the overall effect of the prism is that the prism has changed the direction of the ray at an angle of 180 degrees. So this is what I have written there. So the direction of the ray has changed at an angle of 180 degrees. So my dear students, by this question, we have reached the end of this paper. So I hope that this will be helpful to you. This video is helpful to you. If you find this video helpful to you, don't forget to subscribe to my YouTube channel. Don't forget to like this video. And if you think that this video is helpful to you, this is helping you to understand the paper, ATP paper, and this is helping you to prepare for your Cambridge exam. Share the link of this video with your class fellows and with your other friends who are in O levels. So this will be a great appreciation for my channel, for my work, and that provides fuel and energy. And then I get motivated, and I can make these videos. So I'm hopeful that I am to some help to you. So thank you very much, everybody. It was a great pleasure teaching you all. So thank you very much once again. Thank you very much once again, and have a good day. And God bless you.